Good morning, everybody. It's great pleasure to have a chance to do preliminary talk. My name is Masao Arakawa from Kagawa University. Today, I'd like to talk about how to design heuristic search. To begin with, before CJKOSM1, there's one conference called Second China-Japan Symposium on Optimization of Structural and Mechanical Systems. It was in 1996 in Beijing. At this conference, I was the first speaker of all of the session, which is going to be held first day afternoon. Before that, we have a 2 preliminary talk, and also there's a big lunch. And Chinese society serves Chinese wine, very strong ones. I was very nervous because I was the first speaker, but everybody got drunken when I like to start to talk. So everybody just open up their mouths and sneezing. That's my first opportunity to join this 2 countries symposium, and I was very surprised about it. And you know, today I'm talking in my office. It's pity that I lost chance to meet all of you at face-to-face. But this is probably only the way that we can have conference like this. And I would like to thank to all the Korean society to keep this conference. And at CGKOSM1, I talk a little bit about adaptive genetic algorithms. Today, I'd like to talk how to design these new algorithms. It's a long story. I started to work on genetic algorithms maybe in 1991 or 1992. And in 1994, I wrote my first GA code for topology optimization. And result comes like this figure. It seems it's better than the other person. There are a lot of them working on this field at that time. But it cost me 300 individual and 180 generations. A lot of function calls. But if you make some simple rules, we can have solution like this with only in 8 analysis. We don't need to do a bunch of analysis to have topology optimization, which is very shocking for me. At the same time, there's one research seminar at Tokyo Institute of Technology. And at that time, the speaker was Dr. Ishii at Quint. And he introduced us OptiShape. It was very fascinating because I thought homogenization method is very difficult. So that I go into GS type. But with his explanation, it is not so complicated. And his software seems very fascinating. So I gave up topology optimization in genetic algorithms. And I became against 2GAs because it is difficult to handle continuous numbers. And in 1995, Professor Panos Papalambos insisted that mixed variable problem is most daunting problem. And I agree with him. And most likely in mechanical design, we have to treat with mixed variables. Thus, GA has no chance to go for it. Besides, in GA, it is very difficult to handle constraints. And most likely, optimal solution becomes intersection of several active constraints. Once again, I thought it is very difficult for genetic algorithms to become a good method. Talking about simple GA, we have a lower limit and an upper limit. And of course, certain number of bits, we have some digit. And this is trial of a Rosenblock function with the number of bits and the number of design variables. Of course, if we don't have much design variables, we can truly have solutions. But as number of design variables lies and also bits lies, it is very difficult to have good convergence. And if we don't set our number of bits, their accuracy becomes real low. So take a look at this, then please think, are there any range that is good for simple GA? Probably it's around here. If we have a lot of number of bits, GA doesn't work as we supposed to have. At that time, most of them said that GA is good for large-scale combinatorial problem. But as you see, it is not. So it's a kind of phantom or something. GA, it works well only in a middle size problem. Or of course, smaller size works better. So we have to think the other way. So key for the success in heuristic search almost always lies in a combination of convergence and diversity. As for simple GA, there is a elitism for selections, for convergence, and also roulette selection for diversity. At the same time, smaller number of population and big crossover is good for the convergence, and huge population with small crossover is good for the diversity. Small mutation is good for the convergence, and big mutation is good for the diversity. There's almost always a conflict each other. And if we tune it better, it sometimes works better. So as the situations goes by, we have to change the mode for the convergence, sometimes for the diversity. This is very complicated point to design heuristic search. If we compare simple GA with BLX alpha, BLX alpha doesn't have gene. They randomly choose from the area that they have given by two parents. And if we don't have any mutation for BLX alpha, the solution is very, very ugly, especially when the number of the design variables become higher. In this case, even in the number of design variable is 8, we don't have a chance to get good solutions. Lots worse than simple GA. And some says to express continuous number, it's much better not to use gene. But as you can see in this table, gene works better than random search. So this is comparison of how it goes. As you can see, convergence is relatively dull. But with the information of gene, we can have a much better convergence and getting out of local optimum to have good solutions. So gene has some function in searching for sure. And what do we want for the heuristic search, genetic algorithm? We would like to have high convergence. Then it's better to use gene. And we would like to make a problem in a middle scale. If we would like to have higher accuracy, we should have to put more and more bits for one design variables. But if we did it, problem became large scale, and it is not good for the convergence. So we have to do something to overcome this conflict. High convergence versus high accuracy. So take a look at this digit. If we at least need these digits, we have to put a lot of bits here. And this one, small number of bits, and scale become middle. That's why it is much better for the convergence. But if and only if we can shrink the searching range, with small number of bits, we have the same digit as in the red one. And if we can shrink the searching range even more, we have more accuracy. So we have to think to find out how to make searching range smaller and smaller, which means we have more accuracy. And truly, it can be treat continuous variable. By nature of genetic algorithms, if it finds local minimum, it tends to gather a lot of individuals there, which means their standard deviation shrinks. And if we use this information, we can tighten searching range smaller and smaller. This is what I thought when I began to think about adaptive range genetic algorithms. With adaptive range genetic algorithms, of course, it needs to have a lot of parameters to keep the searching range within good position. The result is much better and faster than simple GA or BLX alpha. Take a look at here. The generation we needed is much smaller than these. Same here. And same here. But if the number of design variables lays, they don't have any more high convergence, but we still can keep high accuracy. But if they become 100 over 100, becomes very difficult to keep algorithm better than simple GA, like here. But with new mutation, we can have a little bit better than simple GA. So difference between without and with, and in without, we only use general mutations. And with means we randomly generate population individual and put it into the family. And we call it as immigrant. So with immigrant mutation, we have a little bit better result compared with simple GA. And thinking of these things, simple GA is simple. Therefore, it is robust. An adaptive range genetic algorithm, we have to think more and more ideas to keep it strong and robust. As you can see in the comparison of convergence here. So I would suggest you 4 points to make heuristic search. Especially in GA, you have to keep your GA as simple as possible. Your effort works well if your scale is relatively small. If you put so many complicated ideas in it, it becomes difficult for you to control them. So you have to minimize your effort. And for the large scale problem, think to make smaller so that it works just as a middle scale problem. And the idea is just like building block for the simple GA. And convergence goes by, you can fix some part. Then it becomes smaller. Its scale becomes smaller and smaller. For this idea, one of our junior students is going to present his idea in this conference. So please look at his video and you will see how it works. Unfortunately, there's some shortcomings in GA and probably most of all heuristic search. It's a number of function calls. It is relatively large. Honestly, very, very large. For that purpose, I would like to suggest to use surrogate model for GAs. And in my case, I propose convolute RBF, which works very well. And I would like to show you one example about it. First of all, we do some sort of data distribution and go into the analysis and make a surrogate model and compare this reference value. We make satisficing method to scalarize objective function and use GLGA, and we found best 3 peaks and also recommendation function to make new points. And we continuously repeat this process again and again until we get satisfied with the results. To see the efficiency, we use a numerical example. That is parameter given by Young's modulus, Poisson's ratio, and sharing coefficient. And we choose 12 eigenvalues and their modes. And a conventional way is most likely use least square method, as shown in this formulation. But our ways is quite slightly different from that. We set everyone as objective function from plus side, larger side, and a lower side. So it means with these two objective function, we would like to make both one is quite equal to the value of reference. And this is a convergence iteration. And as you can see, with line search becomes much better than the others, especially compared with response least square method. We have much better value with surrogate model and with line search. And let me show you a little bit about what line search means. As you can see, we have a very good solution without Poisson's ratio. That is because, take a look at this one. This is Young's modulus. And as you can see, true solution is, where is it? Oops, here. And as you can see, we can find some bottom at the right value. Therefore, we can make surrogate model quite easily. And but as for the Poisson's ratio, we cannot see anything about those things. So that we add data through the line like this one. And with bottom value of the other data, and we add some certain number of data, something like this. We seems like just searching in line. Therefore, we call it as a line search. And as we have a very good value by using this model, this method, we actually use to the motor. And as you can see, we have to have a 14 different material IDs. And we would like to make error within 5% with experiment data. And this is how it works. Experiment data is these one. And these one are given by FEM analysis. We ask some expert to give Young's modulus, Poisson's ratio, and sharing coefficient, something like that, all 14 material IDs by expert. And this is a result. Unfortunately, they cannot achieve within 5%. But in our method, we can achieve everything in 5%. And also, we have a very good number of markup. Okay, let me talk about PSO. PSO is made by Kennedy and Everhard, and it's simple. And all the formulation can be expressed as these two lines. Okay, let's talk about PSO. PSO is made by Kennedy and Everhard and expressed in these two equations. And key point of success lies in choosing these three parameters. And Professor Yasuda showed us for the stability of PSO, it should be in between 2 and 4. And it is said that if you select good W, C1 and C2, then PSO works very well. And it's true. So that PSO need parameter tunings. But how many times do we need for parameter tunings? We don't know about it. And no one tells us about it. But if and only if we select good parameters, it works very well. But as we know, if C1 and C2 becomes 2 equals 2, it means early convergence. And C1 plus C2 equals 4, it go around somehow global best. So it's once again convergence in diversity. And as you know, it doesn't need every individual has same parameter. If we mix together, it works very well. And also we are free from parameter tuning. So as for the diversity ones, it goes something like this. It doesn't seem to converge at all and going around somewhere very close to global solutions. Oops. And this is for the convergence. As you can see, it converges quickly to local minimum. So if we put together, it goes something like this. Now, quick convergence one got global solution. As a result, we are free from parameter tuning. Almost like every problem, if you choose those two parameters, it works. And this is a result of Rosenblock function and a Neustrian function. As you can see, if the number of design variables is small, it works very well. But it doesn't when number of design variables becomes large. So how do we do that? GA has mutation, and adaptive lane genetic algorithm has immigrant mutation. Let PSO have the same mechanism. Then how? If each individual's velocity became close to 0, they have no chance to improve anymore. So let's get out of there. We call it as explosion. We can choose place anywhere randomly, and then they can come back again. So this is with explosion. As you can see, we have a better solution than without it. So interesting part of heuristic search is each and one heuristic search has its own strong point. And combination of them are infinity. For example, let me talk about one example, plot planning. Ordering GA, rule selection GA, and tweaking by PSO, and candidate finding by ACO, and selection by simple GA. At the time being, we only show the plot planning part. So we have made some selection of angle and maintenance place according to this 4 candidate or 3 candidate, and rule for selection of target by this way. These are all made by simple GA. And as for the ordering, if we have ordered something like this, and everyone can take 0 degree and 1 for the target, and then it goes something like this. And once you get this final one, and go to PSO to tweaking, and then it becomes something like that. If we first started from PSO, we can never have solution, something like this. So this is trying with actual plant. Expert make this solution, and GA make this solution, and PSO, after PSO, we have solution, something like this. It is very close because expert is expert, and they know very close to the optimum solutions. But looking at the value, it's much better than skilled designer, even more in PSO. Thank you for your attention, and I'm pleased to answer any question.